All right, let's do it. So our question is, determine if this matrix is singular or non-singular. So let's just talk about definitions of singular versus non-singular. Singular means that Gaussian elimination essentially doesn't work, and non-singular means that it does. All right, let's do it. So let's do some Gaussian elimination to see if it works. What I mean by it working, I mean that we actually end up with a matrix that's full rank. We end up with a matrix that has all the pivots. So yeah, let's try that. So let's apply the algorithm. The algorithm, we start with this one, then this one, and we're just gonna get each of those to be a 0. So we're rotating. Okay, let's do it. Step 1, we need to get the 7 to be equal to a 0. So if you want to do that with Gaussian elimination, sometimes I set up an equation to help me out. So 3 times x, so what times 3, plus 7 equals 0. Subtract 7 from both sides, negative 7 divided by 3. The x equals negative 7/3. So that's what we're going to do, is we're going to do row 1 plus negative 7/3 row 1. Plus row 2. And let's see what that looks like. Alright, let's write the ones that don't change. Since we're only messing with row 2, we leave row 1 and row 3 the same. And we do negative 7/3, first row, element 3, plus that element in the second row, 7 equals, let's see what it equals. 3's cancel, negative 7 plus 7, 0. That's what we wanted, so perfect. Next, negative 7/3 times 5 plus 9 equals 5 times negative 7/3 is 35 thirds plus 9. 9 times 3 is 27, so I have 27 thirds equals. So 35, negative 35 minus 27, 15, 7, it's 8, it's clearly 8, so negative 8 is our answer. I mean negative 8 over 3, so that's what this one is, negative 8 thirds. Next, we have negative 7/3 times 2 plus 3 equals 7/3. 7/3 is 14/3 times 2 is 14/3. 3 times 3 equals 9, so plus 9/3. So 14 minus 9, or negative 14 plus 9, and 4, 5, negative 5/3. Alright. Next, we need to get rid of the 2. How are we going to do this? So we went down 1, let's go across. Just so we don't get 2 lost. So 3 times x plus 2 equals negative 2/3. Negative 2/3 R1 plus R3. Write down the rows that don't change. Now the last row. 2/3 row 1, which is 3, plus 2. 3's cancel, negative 2 plus positive 2, 0. That's what we wanted, 0. Negative 2/3 plus times 4, wait, times 5, top row, plus 4, the bottom row, equals -10 thirds plus, so we just do 4, and we can times it by 1, which is 3 thirds, so 4 times 3, 12 thirds, equals a good old 2 thirds. -2 thirds times 2. It's 4 thirds, -4 thirds, plus 3, which is 9 thirds, equals 5 thirds. All right. Now we're going to do we have 5. No, we're going to do, well, we can't do the top row, we have to do the next row. -8 thirds x plus 2 thirds equals 0. Subtract 2 thirds. We have 8 thirds times by -8 thirds. And by the reciprocal, which is 3/8. That will cancel this. So 2 negatives, that's cancel. So we're just doing positives now. So 2 and 3 is 6. And 3 and 8 is 24. 6 is a multiple of 24. So 24 is 12 times 2, which is also 2 times 6. So we can cancel the 6's. We're left with 1 on top, 1/4. X equals 1/4. So 1/4 row 2 plus row 3. All right, let's write down the ones that don't change. 5, 2, 0, -8 thirds, -5. We can just stop right now because I have a feeling this is just going to work out. But so we have -8 thirds R2. Yeah, 1/4 times -8 thirds. I wrote this in the wrong order, but it's still fine. Multiplication is communicative. Communicative. Plus 2 thirds equals 8. Well, we're multiplying them, so we can cancel 8 and 4. Get rid of that. 8 divided by 4 is 2. 2 thirds plus 2 thirds, -2 thirds plus 2 thirds is 0, which is what we wanted. One fourth plus times R2 -5 thirds times 5 thirds plus 5 thirds equals 5/12 plus 5 thirds. What can we times 5 thirds by? Well, we times by 1, 4/4. So we end up getting 12 on bottom. 5 times 4 is 20 on top. Okay. 20 minus 5 is 15. 15/12. Okay. So even if we didn't get everything perfectly right, it looks like Gaussian elimination worked. We didn't end up with a row with all zeros. We were able to get this into upper triangular form. And a reminder, upper triangular form is where we have numbers here, and we have zeros down here. That's what we're able to do here. Depending on the shape, that's how many zeros you have. So in our case, we have 3. We're able to do it. Therefore, this is non-singular, according to the definition in the Applied Linear Algebra book. All right, well, zoomed out a bit, but ignore that. That's all for today.